Other questions? No, there is of course no time translation invariance. That is one statement, right? But the other statement, let me write down the metric, right? So we had this form of the metric, which is minus f1 p dt square. This we saw is x independent. Okay, this was the form of the metric we had. Okay, and then the statement was this, of course, has no time translation invariance because things depend on time. Okay, but what I said is that this one has isometry. Okay, and those isometric transformations take the form of xi going to, let me use a different symbol, phi I of x, the isometries. And these have no time dependence. Okay, this phi I of x cannot have time dependence, because if it did have time dependence, then under these transformations you will generate the F2 IT component, right? And we know that this original metric doesn't have the IT component, right? So in order that this is an isometric, these transformations should be XT independent. Any other question? Okay, so let me start with this. Okay, and we will try to fix the form of the various functions by using what we know about maximally symmetric spaces in 3 dimensions. No, we saw that it is true, because the this 3-dimensional metric, right, has 6 isometries, right? And that, okay, then I am using the fact that n into n plus 1 by 2 in an n-dimensional space, n into n plus 1 by 2 is the maximal number of isometries that you can have, right? So in 3 dimension it's 6, right? So you have got 3 rotation and 3 translation, right? That's why it's maximally symmetric. Exactly. So you have 6 scaling vectors. That's the maximal number you can have in 3 dimensions. Yeah, homogeneity and isotropy depend. I mean, basically leads to the fact that this 3-dimensional space is maximally symmetric. So that's an assumption that we have homogeneous and isotropic metric. So the first thing we can do is to get rid of this function f1t, and that is defined by using a new time coordinate. Use new time coordinate. So okay, so in this form it's clear that f1 of t has to be positive, right? Otherwise the metric component will not have the Minkowski signature. So you use new time coordinate t prime such that is defined by differential equation dt prime is equal to f1 of t dt. Okay, if you want to write explicitly, then a t prime is some t naught to t Okay, so this defines t prime as a function of t, right, up to a shift, because t naught can be changed. And then, so that basically writes this metric as minus dt prime square plus this with t written in terms of t prime. Is this clear? So effectively, then we can forget about this F1. Right? F1 can be removed by a change of time coordinate. Okay. And so far, we have not been touching the time coordinate. Okay. But you see that this kind of transformation leaves constant t slices unchanged, right? Constant t and constant t prime are the same, right? Because t prime is only a function of t, right? If it involved x, then there will be a problem, right? But because t prime is a function of t only, if t is fixed, right, then t prime is also fixed, right? So the constant t slices are get mapped to constant t prime slices. So the notion of homogeneity and isotropy that we have been using also holds for constant t prime slices. Is that clear? Yes, will change.
And will it still remain? Will still have those isometrics it had earlier?
It's okay. The form of the isometric transformation may change, but as we discussed, that change of coordinates doesn't remove isometries, right? Okay, so the form of the transformation may change. Yes.
And now we know that this new t prime has.
Yeah, well, I mean, I'll call this new t prime cosmic time. Because cosmic time, how do we define cosmic time? That the constant time slices have the homogeneity and isotropic property, right? So microwave background has the same temperature at constant time slices, right? There, whether you take constant t slice or constant t prime slice, it will have the same property, right? Because constant t corresponds to constant t prime. Right? If it involved x, then that will be a problem. Right? If the relation between t and t prime involved x, then constant t will not correspond to constant t prime. Right? It will be some function of t prime and x that will be constant, right? But because t and t prime are just related without any x dependence, constant t and constant t prime slices just get mapped to each other. Okay, so you can just use t prime as my new cosmic time. Okay, so we rename t prime as t. And write this and F3 appropriately. Because when you change t to function of t prime, right, the functional form of F3 will change, right? But that's new object is what I'm going to call F3. So I'll write as minus dt squared plus F3 dx. Yes. The functional form of F3 will change.
The number of isometries won't change.
No.
Is it possible that the kind of isometry it has, that changes?
It is in principle possible, right? But here it doesn't happen because we saw that the isometries, right, are t independent. So the form of the isometric transformation is the same as at all t, right? So whether you would call t at whether you work at t or some another time, it's the same isometric transformation. Right? And because of this, the changing from t to t prime, right, doesn't change the form of the isometries. Right? If originally it was independent of t, isometric transformations, now also it remains independent of t. Right? Because independent of t means independent of t prime. Right? And that new t prime I'm calling t. Right? You can also see it directly from here, right? If you start with this metric and demand that you have an isometry, right? If the isometric transformations are depending on t, then you will again generate the tx component. Right? Original metric doesn't have that. Is this clear?
Changing the kind of isometry, what does that mean? Right.
He's asking whether the isometric transformations will change. Right? And I'm saying in principle it could change under coordinate transformation, right? Because
that's the same isometry in some other coordinates.
Exactly. Yeah. But in this case, even the functional form will not change because the isometries we had seen are independent of T anywhere, right? So because of this, in this case, even the functional form remains unchanged, right? Even though the functional form of F3 itself would change, right? Because of this changing from T to T prime. Any other question? Yes. Functional form of F3 can change, right?
Cartesian coordinates. Here the translations are x going to x plus a. I will do x plus b. Then I go to polar r theta phi.
Yes, there of course it can change, right? But here you are only changing T. See, if we are changing x, then indeed isometric functional form will change, right? But this change that I am making here is just changing T, right? Keeping the x fixed, right? So I should have written this x prime is still x. So because of this, the functional form doesn't change.
If I think of the 3D slices as like something which is varying with time, each time has a different way.
Yes.
But when we are redefining the time, you are saying that these definitions will just be in different
Exactly.
definitions, but actually the metric structure of the 3D surfaces won't be.
Exactly. And the point is, because of these different time slices, right, the isometric transformation was the same because it was T independent, right? So whether you are doing the isometry on this slice or that slice, right, the metric is different, but the transformation is the same, right? That's why calling T a T prime doesn't really affect the form of those isometries, right? But in any case, the point is, you have not said anything about what those isometries look like, right? So you are not losing anything. Even if they changed, I'll just work with this metric and ask for isometries. Okay, so now I'm going to tell you what are the maximally symmetric spaces in 3 dimensions. Okay, because I'm not going to prove that there are only those 3, right? But this is something that one can show. Okay? I'll just use the result that the maximally symmetric spaces in 3 dimensions are all classified. And those are basically flat space, hyperbolic space, and sphere. Okay, and we will describe in detail what exactly those mean. Okay. So, maximally symmetric spaces. In 3 dimensions. The first one is just flat space. Okay, metric has is dx square plus dy square plus dz square. This one is clearly homogeneous and isotropic, right? You can just translate and you can rotate. The second one is a sphere, okay, but a 3-dimensional sphere, okay, which is labeled by x square plus y square plus z square plus w square equal to r square, okay, where r is some constant. Pardon? But it has a constant, right? So we are using 4 coordinates with a constant. So you can just eliminate w, right? Okay, so this is a sphere embedded in Euclidean space. So I'll write ds square as dx square plus dy square plus dz square plus dw square. This is the original Euclidean space. Okay, but then you can just eliminate w using this, okay, and get a 3-dimensional space, right? Just like we defined the surface of a 3-dimensional sphere as x square plus y square plus z square equal to r square, right? This is one higher dimension, right? So that's a 3-dimensional sphere. Okay, so you are going to write down the metric in a convenient form in a minute. Okay. But first, let's try to understand why this is homogeneous and isotropic. First, let's try to understand whether it's homogeneous, right? So what is the criterion that given any point on this sphere, right, there should be a transformation that takes it to another point. Right? That means given x, y, z, and w, and x prime, y prime, z prime, w prime, right? Each of which satisfies this, you can go from one to the other. Right? Yeah, without changing the form of the metric, right? Which is induced from here. And that is simply implemented by 4-dimensional rotation. Right? So if we take x, y, z, w, goes to s times x, y, z, w, with s transpose s equal to identity. This is a generalization of the 4-dimensional rotation, right? Rotation in 4 dimensions, which rotates among these 4 coordinates. Okay. Then it's a general result that 2 vectors of equal length can always be rotated to each other. Right? There is in 3 dimensions, it's familiar, right? If you have 2 vectors of equal length, right, you can always find a rotation that takes you from one to the other. Right? So there is a generalization of this in 4 dimensions, that if there are 2 vectors of equal length, then you can always find a rotation that takes you from one to the other. Okay, this is what shows that this is homogeneous, and this preserves the metric, right? A rotation like this, right, because of the S transpose S equal to identity, it will also leave this unchanged. Right? So even without writing the explicit metric in 3 dimensions, right, which I'll be doing soon, we can see that this space is homogeneous. Right? Surface of a sphere is homogeneous. Right? It's easier to see in the embedding space, right? Like for example, in suppose you have a 2-dimensional sphere, right? You write a x square plus y square plus z square equal to r square. Then it's clear that you can go from any one point to any other point by rotation. Right? But if you write it as d theta square plus r plus sine square theta d phi square, right? In that form, it's not so obvious, right? Because it doesn't look, all points don't look symmetric, right? In that form, d theta square plus sine square theta d phi square. Theta equal to 0 metric looks different from theta equal to pi, or theta equal to pi by 2. So embedding coordinates are usually easier to visualize symmetries.
This is sort of global structure of the sphere is also playing a role.
Exactly, the global structure is manifest in this case, right?
Because we need any 2 points to be connected by a rotation.
Exactly, that's right. Meaning we need any 2 points to be connected, because if we want isometry, if we want homogeneity, and rotation does the job.
Yeah.
Okay, that's what we are using. Is this clear? That is next step, isometry. That comes from the isotropy. See, the homogeneity is given any 2 vectors, any 2 points on the sphere, you should be able to go from one to the other. There, the length didn't play any role, right? Given any 2 points, you should be able to find the isometry, right? The second part was that you have that if you have 3 points, right, 2 of them being equal distance from the 3rd point, then you should be able to find an isometry, right, which keeps the 3rd point fixed and takes you from the 1st point to the 2nd point. Right? That we'll now see how to do. Is this clear? So this implements homogeneity, right?
This matrix S.
Yes.
How many independent components?
6.
But it's only taking care of homogeneity. Should be done by.
Yeah, because it's redundant, right? Given think of on a 2-dimensional sphere, right? If you want to connect 2 points on the sphere, right, you have to do a rotation, but there are many rotations which can do that. Okay, combination of various rotations, because you 2 points on the sphere, if you want to connect, you only want rotation by phi, right? Okay, but in general, there may be more rotations that are available, right, which can do that. So this is redundant. Okay, but what it is saying, we don't care about the fact that it's redundant, that there is at least a transformation that takes you from one to the other. Yeah, that because it's induced from here, right? So if you apply this transformation, right? This also remains unchanged. The same proof that this is unchanged, right? Dx dy dx. So dx dy dx dz dw will also transform in the same way, right? Because it's S doesn't depend on x, y, z, w, right? It's a fixed rotation in the space. So this is also unchanged. Right? That's why it's easier to see in this language, right? If we use r theta phi coordinate or theta phi coordinate, right, it is still true that the metric is unchanged, but you have to do a lot of algebra to check that.
All the isometries of the bigger space, we keep the embedding, like the isometries of the smaller.
Yes, indeed.
Constant also.
Constant also has to remain invariant. Exactly. I think that's what I meant by saying the embedding invariant. Right? Yeah. So it has to be, if it's an isometry of the metric and the isometry of the embedding equation, right, then it's automatically an isometry of the of that smaller space. It could have.
So more isometries in the space that has been.
It could happen if then the equation itself will have to break that isometry. See, if this is, if the embedding space is an isometry, that means this has an isometry, right? So something has to break it. The equation, the constant could break it. If you change the x squared to 2x squared, for example, right, and keep the metric like this, then it will not have the full isometry. Is this okay? Now, isotropy. As we discussed, once you have proven that the space is homogeneous, okay, then to prove isometry, it's enough to prove that it's isotropic around one point. Right? You pick any point in that space, and if you can prove that the space is isometric, isotropic, that's good enough, right? Because then you can use the homogeneity to move the points. Okay. So we choose a point. Okay. To choose the point, zero, zero, zero r as x naught. I think what we call this x naught, right? And the x1 and x2 you have to choose. Very clear? This is a point on the sphere, right? It satisfies this equation. Right? So if you can prove isotropy around this, we are done. Now we have to choose two other points at equal distance. Right? So let's take x, y, z, r, z not r. Here it should be r square minus x square minus y square minus z square. For the x1, y1, z1 and x1, y1, z1. And x2, y2, z2. These are two arbitrary points I've chosen. Okay, the last component has been fixed so that it satisfies that equation. Is it okay? But you have to impose some other condition, right? Because these have to be equal distance from this. Right? We want these 2 points to be at equal distance from this. So what is that condition? Under what condition these 2 points will be at equal distance from this? I don't have angle. I only have these variables. Right, same angle on the geodesic, right? If you take a north pole, suppose you take a north pole on the sphere, right? So you are asking which points are at equal distance, right? There is, well, diametrically opposite points are very special cases, right? We want a general class of points, right? Given one point, suppose, okay, let's put it this way. Take the north pole, right? Choose another point arbitrarily. What are the other points that are equal, that has the equal distance from north pole? Right? You have to draw this small circle, right? Slice it, and everything on that will have equal distance, right? Okay, same theta. If you use theta phi coordinate, theta equal to 0 is the original north pole, right? Same theta will have equal points at equal distance, but we are not using theta phi, right? X, Y, Z. So suppose now think of the sphere as in the X, Y, Z coordinate. We are at 0, 0, R, right? At Z equal to R, X and Y 0. We pick another point, okay, X1, Y1, and square root of R square minus X1 square minus Y, right? What other points will be at equal distance, right? If you take X1, Y1, and X2, Y2. Same? Same of this. These coordinates should be the same. That's the intuition, right? Same height. That's what I said, right? When does that happen? That happens when x1 square plus y1 square plus z1 square will be x2 square plus y2 square plus z2 square. Because if these two are equal, then their lengths better be equal. Okay. So what this is doing, right? I mean, this intuition, right? You can think of it this way: that in the embedding space, right, we have a point, right, which you can call a north pole. Okay. And in the embedding space, you can calculate distances, right? It's Euclidean space, Cartesian coordinates, right? So x1 minus y1 square, x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square plus w1 minus w2 square, right? These are distance in the embedding space. Okay. These are not the distance on the plane, right? Because that has to be by geodesy. But if two points are at same embedding distance, same distance in the embedding coordinate, right, from the north pole, then it's not hard to see that they'll also have the same geodesic distance. Right? Again, use the intuition on the sphere, right? When you say same height, right? What is the intuition? That in the Cartesian coordinate, if you just directly draw the chord, right, they are the same length, right? The direct Cartesian distance. So as long as the direct Cartesian distance is the same, right? The on the sphere, right, along the geodesic, also the distance will be the same. Okay. So if you want, you can write down the metric and calculate this. You can calculate the metric, write down the metric on the induced metric and calculate the geodesic distance. Right? But intuitively, it should be clear that these 2 points will be at equal distance, okay, provided these vectors have the same length. Then the heights will also be the same. Okay, so we put x1 square plus y1 square plus z1 square equal to x2 square
By the way, it should be in general too, right? If I have some induced metric, so if something is equidistant in original metric, then metric also.
No, it's not always true. It's not always true if you have if you don't have symmetric spaces. Imagine that you have a very complicated surface, right? Okay, on a complicated surface, I mean, the original distance may be the same, but along the geodesy, the distance may differ, right? Here, because the space is symmetric, right, that's why these distances are the same, right? Equal geodesic distance also means equal distance in the embedding space. Yeah, so we'll do the hyperbolic one in a few minutes. So now, what do you have to prove now, right? To prove that this is isotropic, you have to prove that there is an isometry that leaves this point unchanged and takes this to this, right? Because that's what the isometry is supposed to do, right? If you have isotropy, right, it should leave the x0 unchanged. This is our x0, this is the original point, and it should take this point to that point. So what do you do? What kind of transformation should you use? Yes, 3D rotation, right? If you use a rotation that acts only on these three, not on the fourth one, right? Then clearly this will remain unchanged, right? And it will take this vector to this vector. They have the same length, so there is always a 3D rotation that can take from here to here, right? And it leaves this unchanged. Okay, so let me write down the matrix. It should become clear then, right? What this transformation is. So it use the transformation x, y, z, w, going to, we call it something else, v, 0, 0, 1. Okay, block diagonal form. So V is a 3 by 3 matrix. With V transpose V is equal to identity. It's 3 by 3 identity. Okay. So if you take this matrix and apply it on this, it leaves this unchanged, right? Because it's block diagonal. So V acting on the 0, 0, 0 gives you 0, 0, 0, and the 1 doesn't change this R. When it acts on this, right? Again, because it's block diagonal, these two are not touched, right? But they are equal anyway, so you don't have to do anything, right? And it acts as a rotation on x1, y1, z1. And we know that there is always a rotation, 3-dimensional rotation that can take from here to here because they have the same length. Is this clear? Yeah, so that's what establishes isotropy. Yes, yeah, exactly. Radius is this one. In this case, the radius is x1 square plus y1 square plus z1 square, right? Exactly. 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 So this, that's why the counting worked, right? This S had 6 parameters, right? So that's why S, see the point is these are special cases of that, right? Okay, so the S does the job of both homogeneity and isotropy. Okay, the 4D rotation. That's why the surface of a 2-dimensional sphere is also homogeneous and isotropic, right? And what achieves that is the 3-dimensional rotation, right? Which has 3 parameters, right? 2 of them go for homogeneity because here is 2-dimensional. You have to go from one any point to any other point, right? So 2 of them go for homogeneity and 1 goes for the rotation, right? Isotropy in 2 dimensions is just 1-dimensional, right? That's our rotation about the point. Okay. So the rotation matrix in this case takes care of both.
Just like that, if you choose a reference point, for homogeneity, we should be able to connect that point to any point.
Exactly.
But so then this matrices which implement isotropy, these are exactly the redundancies.
Exactly. That's right. Right. So suppose you want to go from A to B, right? You found a matrix that goes from A to B. Okay. But now you multiply by another matrix which keeps B unchanged. Right? That's the redundancy, right? That also takes you from A to B. Yes. Exactly. ISO 3, 1, ISO 2, 1, right? Is sorry, yeah, it is Euclidean, yeah. Whatever that group is called, right? But there are 6 generators in that group. 3 translations and 3 rotations.
We are after maximally symmetric spaces and we know the maximum number of isometry. So once we see that all the all the isometries of the bigger space, which keeps my equation same. If they exhaust that number, then we know for sure we have found out all the isometries.
Exactly.
But if my space is not maximally symmetric, then we won't be able to. Will this argument what that if I find out all the transformations of the bigger space, my embedding sense, will be able to.
No, it may not happen, right? Because embedding, after embedding, you may get new isometries. Yes, a bigger space may have a very complicated metric, right? And you embed something, right, which has the metric of a sphere. So it is not necessary that the embedding isometries of the embedding space will generate all the isometries. In this case, you are sure because you have 6, right? We know that you cannot have anything more than 6. Yeah, if you are looking for a maximal symmetric space, right, then the embedding space, there are clear indication of knowledge of what the embedding space should be, right? What is the minimal embedding space, right? So you can always put add more dimensions, right, to the embedding space and put more condition. Right? Add a new coordinate x, y, z, w, say v, right? And say that besides this, we have a v equal to constant. Right? Clearly, that is also doing the job, right? You can make it more complicated. Yes.
The group of
yes.
matrices. What is the implication?
Yeah, the implication is that the S is clearly an isometry, right? Yeah. And S had already 6 generators. Yeah. Right? We know 6 is the maximal number. Right?
So we cannot get new.
So you cannot get new ones. Right? So it better be that S already contains also the ones that is needed for isotropy. On a sphere, yes. On a sphere, of course, sphere is homogeneous and isotropic, right? But homogeneity does not always imply isotropy. Right? You can have 3-dimensional spaces which are homogeneous, but not isotropic necessarily. On sphere, it is, yes. On sphere, sphere by construction is both homogeneous and isotropic. Yes.
Here when we do this kind of answer,
see, here there is no equal length anyway, right? There is no length, no notion of length. Here is a mapping between 2 points. This one, see, it looks like length because you have a embedding space, right? But if you think in terms of the surface of the sphere, right? There's no, for discussing homogeneity, it just says if given 2 points, right, they should be mapped to each other. There's no notion of length there, right? It's only for isotropy that you have a notion of distance, right? That you have to have 1 point x0 and 2 other points x1, x2 at equal geodesic distance from x0. Right? And then there should be a transformation that leaves x0 unchanged and takes x1 to x2. See, here it looks like that you are preserving length, right? Because that length is a 4-dimensional length, right? From a 3-dimensional perspective, these are just 2 points, right? That are being mapped to each other.
you're just taking 1 point to another point.
Yes, you're just taking 1 point to another point. Is this clear? Okay. So what I'm going to do now is to write down the intrinsic metric, right, in this space, because once you have understood the symmetries, right, we want to write down a 3-dimensional metric, right? We don't want to always write 4 coordinates, even though it's sometimes useful. I'm not sure where that has disappeared. Under my notebook. Oh, thank you. Oh, I see.
The equation of chord, the distance along the chord that we are using. Here we can sort of visualize it in the case and then like, but in complicated spaces like hyperbolic space. when let's say we are embedding some much, how is this diffuse?
Well, even I mean, as long as it's maximally symmetry, you can just use symmetry intuition to so that it is true. But you don't have to make it work. I mean, you can always calculate geodesic distance if you want, right? But I mean, once you have fully symmetric space, you can use the intuition.
Distances will be same between those points in induced space as well.
In
Induced space.
but that is only true for symmetry when you have enough symmetry, right? Otherwise, you can imagine a complicated embedding, right? Where the distance and the chord may be the same, right? But actually, geodesic would have different lengths. Yeah, so this intuition works only for I mean, when you have sufficient symmetry. Right? And if you don't want to use the intuition, you just calculate the geodesic distance. Okay. As long as the distances are small enough, right, then the geodesic distance is the same as the chordal distance. Right? After all, we are defining the distance as dx square plus dy square plus dz square to dw square, right? So for infinitesimal separation, two are the same by definition. Right? But it's only when you go to finite distance that they are not the same. Okay, so now intrinsic coordinate. So for this, let me write down the coordinate transformation. So suppose you take these definitions. Then it's easy to check that w squared plus x squared plus y squared plus z squared equal to r square. This just solves this equation. You can probably already see, right? If you add the squares of this, the sine square phi plus cos square phi gives you 1. Right? You have this. Then you add to this the square of that. Then the sine square theta plus cos square theta gives you 1. You're left with r square sine square psi and r square cos square psi. So total gives r square. Yeah, so these coordinates project, these are three coordinates. Now r is fixed, right? So psi, theta, and phi. These are the three intrinsic coordinates on the surface. These are the analogs of a theta phi coordinate on the two-dimensional sphere. Yeah, yeah. That's right, exactly. That's right. Okay, and this is actually generally in the if you have an n-dimensional sphere, right? You can keep doing this and write down the embedding the intrinsic coordinates. Right? You start from r cos psi, then every time you encounter r sin psi, and then cos, then sin cos, and so on. Right? You can go any n dimensions. You can introduce coordinates this way. Well, you can probably do it, but it's better to just write it explicitly, right? I mean, you use theta n, right? And using the theta n, you can write down the series. I mean, every time you add a new factor, right? Except in the last case. Okay, so what is not obvious, but it can, I mean, you have to do this calculation. That you cannot calculate dx square, right? Dx, this is dx square plus dy square plus dz square plus dw square. R is constant, right? So dW, for example, is minus R sin psi cos d psi, right? This one will have a sum of two terms, right? You have to vary sin psi and cos theta. Right? This will have a sum of three terms, and this will also have a sum of three terms. If you calculate all that, square it and add, right? Then this becomes, so this is the exercise. Okay, this also you can recognize the pattern perhaps, that how many you start with d theta 1 square and then sine square theta 1 and then whatever you got from lower dimensional sphere. Right? So iteratively you can figure out what this structure is. Right? This is the metric on the two-dimensional sphere, right? And this is as if you have a two-dimensional sphere, but the d phi, large d phi square has been replaced by another two-dimensional sphere. Okay, so this way iteratively you can figure out what the embedding space metric is. Okay, but we are going to do another coordinate transformation. We define R as sin psi. Looks somewhat strange, right? Because R is normally used as a radial variable, right? But we are using R as sin psi. So R actually runs less than or equal to 1. Pardon? Mod of R, yeah. But I mean, basically, there is an identification that takes R to minus R. Because here not, I mean, there is a restriction on, I mean, what range psi takes, right? But let me write down the metric. Okay, the range will not be very important right now. So with this, d psi square will be dr square over cos square psi, right? Because dr is cos psi d psi. But this I can write as dr square over 1 minus r square. Right? And sine square psi is r square. So the metric becomes r square times dr square over 1 minus r square plus r square d theta square. The reason that I have written it this way is because this looks close to polar coordinates. The flat metric written in polar coordinates, right? Except that for polar coordinates, you would have a dr square, right? Here it is divided by 1 minus dr square. Is this clear? Okay, because eventually we will try to write all three metrics in a compact form, right? Flat metric we know can be written in this compact form, right? dr square plus r square d theta plus r square sine square theta d phi square, right? Here, written in this coordinate system, the only difference is this 1 minus r square in the denominator, right? Otherwise, it looks the same. R squared. So then, yeah, the r will come in the denominator here. Yeah, this will be r over small r over capital R, right? You can do that, right? And eventually we will see that that has some advantage of doing it. Right now, let me keep it like this. That's it, yeah. So the actual range you can figure out because these maps, once you have these maps, right, you know precisely what range corresponds to what range here, right? So using that, we can figure out what the ranges are. Because here, from this, you can check that not clearly there is a restriction on the range of phi, psi, and theta, right? Because different values of phi, psi, and theta, if they represent the same point in the embedding space, then you should think of them as the same. Okay, using that, you can figure out the ranges of the various coordinates, okay, which I'm not doing right now. R equal to plus minus 1? Yeah, that's why, okay, maybe I should say less than 1. Okay, but that is actually R equal to 1 is a coordinate singularity, because R equal to 1 means psi equal to pi by 2, right? Okay, so in this coordinate system, you can say there is no singularity there. Okay, after all, it is a surface of a sphere, right? So there cannot be any genuine singularity. Right? R equal to 1 is just a coordinate singularity. Yeah, so the point is, I mean, I could have taken this capital R here, but I'll do the reverse. I can always take the flat metric and multiply by capital R square. That's also flat, right? I mean, there, of course, it's just it can be removed by coordinate transformation, right? Just by scaling x, y, z, you can remove that R, but I can always add that capital R square. Okay, so let me now discuss the last example briefly. Hyperbolic space. Okay, it's like a sphere, except that I've changed some signs. Is clear? Now, as you know, hyperbolas have two components, right? Two disconnected components, right? That's the same thing here also. So you can see that W equal to plus minus square root of R square plus X square plus Y square plus Z square, right? So W greater than equal to R and W less than or equal to R are disconnected. They are of course isomorphic, they look the same. Less than minus, thank you. So we'll just choose one connected components, right? Choose W greater than or equal to R component. Now, one thing one should worry about is that here the embedding space metric is Lorentzian, right? So it's not obvious from the beginning that the actual space that you have defined is a Euclidean space. So you are trying to describe the three-dimensional space, right? Three-dimensional slice. The time coordinate has already been separated out, right? That has the minus sign. So the three-dimensional metric better have Euclidean signature, right? All eigenvalues positive. It's not completely obvious that this has that property, right? But we'll write down the three-dimensional metric and we'll see that it does have the property. But this is something you may have to worry about, right? You can say, could you have changed two signs here, right? Why not W square plus X square minus Y square plus minus Z square, right? And here also similarly take this to minus X square. But let's try to understand what are the isometries. Any suggestion what the isometries are? a Lorentz group, 3 plus 1 dimensional Lorentz group, right? 3 plus 1 dimensional Lorentz transformation clearly preserves this metric, right? And preserves this condition, right? This is a Lorentz invariant vector. This is basically Lorentz invariant length square of the vector. So 3-dimensional Lorentz invariance, 4-dimensional Lorentz invariance, 3 plus 1 dimensional, right? So X, Y, Z, W goes to lambda times X, Y, Z, W. And W basically plays the role of time coordinate. Is this clear? Okay, so this is a surface embedded in 3 plus 1 dimensional Lorentz, the Lorentzian signature space. But the statement, which I'll prove in a few minutes, is that the embedding space that we have chosen is Euclidean. Okay, it's like a time slice. Okay? Because you have fixed the W, the time coordinate in terms of the space coordinates, right? As you can see here. Okay? That's the intuitive or to see that it's actually a time like the time has been fixed, so it's like a space. It's a space like surface. No, WXYZ is Lorentzian, but the surface that you get after embedding, after imposing this constraint, is Euclidean. Okay? Imagine, okay, let's say a simple example: a normal flat space, right? It has Lorentzian signature, but if you take a constant time slice, that's Euclidean, right? So what I'm claiming is that this slice, this is not constant time, this is not constant W. So W is given as a function of X, Y, Z. This is also a Euclidean slice, right? But we'll actually calculate the metric and verify that this is the case. But before we do that, let's understand the isometries, right? So isometries are this. This is clear. That if you take a Lorentz transformation, right? This obviously this constant is preserved because this is the length of the vector, and this is also preserved, right? Because this is the same minus plus 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 signature. It's just some coordinate in the embedding space. Right? It doesn't have any really physical significance. It's not. It has nothing to do with time. It has nothing to do with time, the real physical time. So 3 plus 1 dimensional Lorentz group. How many generators does it have? 6, right? 3 rotations and 3 boosts. Yeah, that's what we use in special relativity, right? So it is a maximally symmetric space, clearly. We have to check what are the isometry, what are the transformations they generate, homogeneity and isotropy. So how do you prove homogeneity? Given 2 points on the surface, there should be a Lorentz transformation that relates the two. Right? The 2 points on the surface, right, each have equal length. That means 2 points correspond to equal length vectors on the surface. Given 2 equal length vectors, can you always find a Lorentz transformation that takes you from one to the other? Yes? Almost yes, not always. Exactly. So the point is that the time coordinate, right, changing to t to minus t, for example, is not part of a proper Lorentz group. They have the same length, right? 1 0 0 0 1 0 0 0 and minus 1 0 0 0 have the same length, but they are not on the same surface. But as long as they are, the time coordinate has the same sign, you can always find a Lorentz transformation that relates the two. Right? So that information says that given 2 points on the surface, there is always an isometry that takes you from one to the other. Right? Because the points on the surface are related to vectors of length r. Yes, proper part of Lorentz transformation. That you are not including the improper part. I mean, you could try to do that, right? But improper part will mean that you have to include also the other part, other component. Right? The space will be disconnected. Right? We don't want to do that. So it's only the proper part of Lorentz group that is relevant for us.
So it was implicit when we chose the one component.
Exactly. It is implicit when you choose only the one component. Right? That broke the T goes to minus T symmetry, or W goes to minus W symmetry. Is this clear? Okay. So next we have to check isotropy. Right? Again, we can, to check isotropy, once you have proved homogeneity, we can pick any point that we like. Right? For x naught, we can pick any point that we like. Okay. So we pick, so this is homogeneity. Homogeneity is clear. Exactly.
So this is like we have two disconnected paths. So someone can always talk about like if I want to go from one upper hyperbola to the lower hyperbola, this is not possible in this kind of Lorentz transformation.
Proper Lorentz transformation, yes. If you include the W goes to minus W transformation, then it is possible. Right? But we are not using that, right? And we are saying that our space is only the upper part of the hyperbola.
We are just completely removing that.
Exactly. Right? So within that space, it's only the proper Lorentz transformation that is an isometry.
Just one sign of.
Exactly. Right? Just choosing one sign of that is basically doing that job. That we just remove the minus sign here. Yeah. So homogeneity means given 2 points, each of which satisfy this, and each of which satisfies this. That's over Lorentz transformation that relates that, right? No, R is fixed. See, R is a constant because this is an embedding surface, right? We are only using because otherwise it will be a 4-dimensional space, right? Exactly. So R is a fixed constant. Right? So R has the same value, right? Which means that these vectors, if you think of this as a 4-dimensional vector, they have the same length, right? And their time components have the same sign because both lie on this surface. Okay? And then there is a general result that there is always a Lorentz transformation, proper Lorentz transformation that relates those two vectors. Okay? That's the proof of homogeneity. Right? So given 2 points on the same space, you can find a Lorentz transformation that relates, takes one to the other. Translation doesn't preserve this condition. Right? If you take W goes to W plus A, right, just translate, it doesn't preserve this condition. It better not preserve this because then you will get more isometry. Right? You know the 6 is the maximum. Right? So you shouldn't be able to get more than 6. Lorentz transformation in 4 dimensions.
Yes.
Lorentz transformation in 4 dimensions, exactly. So now we choose for isotropy. Okay, this is actually very close to the discussion you already had. We choose x naught to be 0, 0, 0 r. Okay. And then x1 and x2 and x2 is x2, y2, z2, and then last one is r square plus x2 square plus y2 square plus z2 square. Okay, it's identical to what we did earlier, except that instead of having minuses, I have pluses here. Okay, that's because of this condition. right? And again, the fact, I mean, if you want this to be equal distance from this, condition is that this length should be equal to that length. Okay, the 3D length should be the same, right? And then it's clear what isotropy, what generates isotropy. So the isotropy is generated by x, y, z, w. Usual what symbol they use, v. Because it's basically a rotation group, right? This is a vector in the time direction, right? Time, this embedding space time direction, right? Because only the W component is non-zero, and rotation of course preserves that vector, right? If the time component is 1 and space components are all 0, rotation preserves that vector, right? So this transformation preserves this and takes this to this. Yeah, you have to use your intuition. I'm not going to try to describe it. If you don't like the chord argument, you calculate the geodesic length.
Also, we show its homogeneous and isotropic. We are still not sure about signature of the.
Yeah, we are not sure yet. I'm going to do it now. Because for that, I have to calculate the analog of that metric, right? Where did I think I have erased it or here. I have to calculate the analog of this, right? Once I calculate this, then it will become clear what the signature is. Yeah, I mean, that's the intuition, right? Because I have chosen fix the time coordinate in terms of the space coordinates, right? So that's the intuition that it should become Euclidean, but we'll do see it explicitly. I think the analog of the parabolic is a flat space. Flat space lies in between the two. Okay, so all you have to do to find a metric is to change this cos into cos hyperbolic. Okay, you can check that if you change cos to cos hyperbolic, right? Then w square minus x square minus y square minus z square remains r square. Okay, because what is the last step will be r square cos hyperbolic square psi minus r square sin hyperbolic square psi. Okay, I'll write it, but I mean, I'm just explaining in this language that if we change cos and sin to cos hyperbolic and sin hyperbolic, right? Whatever I did for the sphere will go through here. Is this clear? This part, right, is clear. W square minus z square minus y square minus x square will be equal to r square if we replace cos by cos hyperbolic and sin by sin hyperbolic. Here, if we replace sin by sin hyperbolic, that's the replacement that will take place, right? Then this will be 1 over cos hyperbolic, and cos hyperbolic square is 1 plus sin hyperbolic square. So the minus r square will become plus r square. So at the end, that will be the only change. Okay, so let me write this, and then I mean, I'll not explain it very much because it's already implicit in what we have done for sphere. So we write the change of coordinate is w equal to r cos hyperbolic psi Okay, so ds square becomes r square d psi square plus sine hyperbolic square psi So here you change variable to sine hyperbolic psi. Okay, no constant on R anymore. dr square is cos hyperbolic square psi d psi square. That's 1 plus r square d psi square. The metric becomes
One of the
yeah. Okay, yeah. So I agree. So you have to check what maps 1 to 1, right? In this, that if you change the sign of psi and do some other operation on the theta and phi, okay, things may change. So if you say that here theta and phi run over the usual range, 0 to pi, and phi runs from 0 to 2 pi. Right? Using that, you can check what range psi should run over.
then size is 0 to infinity.
From 0 to infinity.
Oh, so here there is no negative R. Like here.
Sphere case, we could have no. I mean, the fact that there is no negative R, that is something you have to check. That comes from the fact that the psi range is restricted, right? On the sphere case, also you have to do the same. There is a sine psi, right? And you have to check if the psi, what the range of psi is. Yeah, there also there will be no negative R. Right? I didn't prove this, but yeah, that is something you have to check. Right? The geometry, what kind of geometry you get.
Here is the R had upper.
Yes, here there's no upper bound, exactly. Yes, here in the sphere case, R was restricted to less than 1. Here there is no such restriction. So these three hyperspaces are collectively written as R square times dr square over 1 minus kr square plus r square d theta square plus r square sine square theta d phi square, where k can take value 0 or plus minus 1. Okay, in the flat space case, I just put this r, right? Because that's the scaling of x, y, and z. Right? I can always multiply the flat space metric by r square. Right? There it's just a coordinate transformation. You can remove the r by coordinate transformation. That's not the case for the other two cases. Yes. This is all plus, right? So that's Euclidean mean not a flat Euclidean space, Euclidean signature, right? All plus eigenvalues. Yes.
There will be more spaces with signatures maybe.
Exactly. Yeah. And those will be, I mean, you have to change some of the signs here, for example, right? To get other signature.
The asymmetrical is also some sort of SO, but
Exactly. It could be SO22, for example, right? Instead of SO3, 1.
is there a similar statement about
Yeah, in 2D Euclidean space also, there are three spaces, right? The flat space, the 2D sphere, and the 2D hyperbolic space. Right? Basically, it's the same generalization, right? You just remove one of the coordinates from x, y, z. Exactly. SO3 minus SO2, 1 are the symmetric transformations.
Different larger dimensions also.
Yeah.
All these three spaces.
Exactly. Right? The sphere, the hyperboloid, and the flat. Yes. That's why maximal symmetric spaces are very constant.
Because when we derive the form of our matrix, we got something like minus b square, then some coefficient times dx square plus dy square plus dz square, which is Euclidean diffusion. And we are looking for the three that maximally symmetric Euclidean space. So this will be all. These three will be the physically relevant.
Exactly. Yeah. So we don't need those for describing our space-time. Right? But that's a mathematical question. You can ask if there are other signature maximal symmetric spaces. Okay. So let me now write down the general cosmological metric from this. Well, that's only by experiment, right? You have to check what of these are consistent with our universe. But that's observation, right? All of these are allowed if we just demand homogeneity and isotropy. So the general cosmological metric is minus dt square, okay, that F1 you have already gotten rid of, plus here you have dr square over 1 minus kr square plus r square d theta square plus r square sine square theta d phi square. And there is an r square, capital R square sitting outside. But that we can make time dependent, right? Because if that becomes a function of time, right, this part of the space still remains homogeneous and isotropic. So I'll write this as a of t square, where this is some arbitrary function of time. Exactly. Right, the time part has factored out. Right, the position space is inside the metric, inside that bracket. Right, because we found the most general metric, right?
We started with maximally symmetric spaces, right? We did that, like how many we calculated, how many we saw these three spaces nicely satisfied all those. But what if like part of it is like one R3, part of is S3? I mean, then these kind of spaces will also satisfy this kind of answer.
Well, but then when they're joining, right, the metric is not maximally symmetric. Right? See, the point is that if part of it is k equal to 1, part of it is k equal to minus 1, right? Then at the boundary, if it is smooth, right, there it's not of this form. Right? It may happen in the universe, right? But that universe will not be homogeneous and isotropic. Right? It will only be locally homogeneous and isotropic.
That might have been the case for our universe, right?
Yeah, it could be, right? We don't know. Yes.
So this homogeneity and isotropy is an effective.
Yes.
It's effective.
Yes.
Where is that information of scale going in the metric?
Oh, we are pretending as if it's valid everywhere, right? But when we find the consequences of this, right, those consequences will be valid only over large scales.
And I mean, there should be some pre-parameters.
Okay, here I have assumed that it's exactly homogeneous and isotropic. So that parameter is not there. It is homogeneous and isotropic at all scales, right? But when you apply it to real universe, right, whatever you get, find as consequences of this will be valid only over that scales. See, because this is certainly not going to know that you have a solar system, right? So that information has not gone in, right? So here I have pretended that the universe is exactly homogeneous and isotropic. That also you have ignored so far, right? That even on large scales, right, there is a small fluctuation, right? That also is not part of this equation. Right? So if you want to know things to that accuracy, you have to change it, change the equations here. Yes, exactly. That's right.
By inserting a k into the
Yes.
when we look at the x3 case, it was this r was less than or equal to 1, before r less than or equal to 1. But the other case will be when we take r in terms of some hyperbolic function, its range could be something different.
Yes, but the point is our universe is such that that boundary you have not, we have nowhere close to the boundary, right? So you don't worry about this. In the sphere, you are right. That if it's actually a sphere, right, the universe is closed, right? If you go far enough, you'll come back to the original point. Right? But that we have not gone, anywhere farther than that, right? So as far as we are concerned, it's, you can think of as infinite.
At large scales, you will our universe will find that.
Yes.
But what about those r's? Will that lead us to some center of?
No. Here it looks like r equal to 0 is special, right? But that's because of the coordinate system that we have used. See, because you have seen that this space is actually homogeneous, right? Any point is equivalent to any other point, right? So yeah, r equal to 0 is no special, thing special, right? We will always do our calculations thinking that we are sitting at r equal to 0.
We can go anywhere, put r is equal to 0.
Change your coordinates, exactly.
Scale from there and or multiple.
Exactly. Okay, now before I end, there's a one intuitive picture that I want to give. So let's suppose you have r equal to 0. This is ours, right? We can always choose up because all points are equivalent, right? R equal to 0 is as good as any other starting point. Okay, suppose you are starting at r equal to 0. And in this three-dimensional space, we want to see how the geodesics look. So to describe the geodesic, I have to give a three-dimensional vector that tells us the initial condition, right? And then the geodesic takes over. So the geodesic in 3D will require giving dxi du. U is some arbitrary parameter, not necessarily affine, right? Because you are okay, maybe let's say affine. We have to give dxi du at r equal to 0, some vector. Once we give these two, then the geodesic is fixed. Is that clear? It is a second order differential equation, right? If you fix the initial x and the derivative, right? Then the second order differential equation fixes the geodesic. So this is a vector that we have to give. But our space is isotropic. Right? This is an isotropic metric. So if we know the result for one direction, we have got it in all directions, right? You just have to make a rotation to get the result in all directions. So let's suppose that Ni is 0, 0, 1. Suppose Ni is 0, 0, 1. And you now let the geodesic evolve. How do you think it will look? X, Y, and Z, you are trying to evolve, or R theta phi, you are trying to evolve, right? Pardon? Yeah, flat it will be aligned, that is clear, right? Flat space geodesics are straight lines. Okay? That is clear? And flat space, if you start with 0, 0, 1, it will just go along the Z axis. Okay? Now let's look at the embedding space. Okay, let's look at the other two cases, k equal to plus minus 1. It's easier to visualize in the embedding space. Okay, because in this card space, I mean, it's hard to visualize. So let's look at the embedding space, right? So in embedding space, we have X, Y, Z, W, right? W is not independent anywhere. W is just given by in terms of X, Y, Z. So if we start with this, right? What do you think? How will the point move in the embedding space? That's how I use your intuition. No, not for the flat case. Flat case, you don't even need embedding space, right? You can use directly X, Y, Z, and you know that it will move along the Z axis. That's a straight line, right? On the surface, of course, you have to lie on the surface, right? That is the definition of a geodesic. But which direction on the surface? Yeah. So 0, 0, Z square root of R square minus Z square plus Z square. That is one answer, right? Is that a correct answer? He is saying that if you take the geodesic, right, it will look like 0, 0, Z, and then square root, right, somewhere. So it's saying it's 0, 0, Z, and square root of R square plus or minus Z square, depending on whether it's a hyperbola or sphere. Right? For a sphere, it will be minus Z square. For hyperbola, it will be plus Z square. Right? So that's the answer that he is suggesting. Right? Is it the correct answer? Yeah, coming back, okay, we can worry, right? First, let's look at the nearby points, right? Yeah, that is of course, geodesic by definition has to lie on 3D, right? So W will be fixed in terms of X, Y, Z, right? But is this the space along which the geodesic will go? This is now a line, right? This is only one parameter, Z. If I say this is the case, then that fixes the curve. Yeah, this agrees. Okay. No, for 2D sphere, what did you say? See, here the question is, suppose you are starting at a north pole, right? And now it's a 2D vector, right? So you have to give the vector on north pole. Suppose it's such that you start your original tangent vector is pointed in along the x direction. Okay. Then the geodesic, right? What will be the geodesic? Imagine a sphere. You start in the x direction, right? what kind of geodesic will you get?
So yeah, the y will still be 0.
Y will continue to remain 0, right? It will be basically the plane, y equal to 0 plane, right?
It's something like this.
So why do you think that is okay? First, why do you think that is the case? Why? How can you argue that y will remain 0? Yes, true. But is there a guarantee that there is? Because it's a complicated nonlinear equation, right? Yeah, embedding space, of course, makes sense. It's flat.
One special type. It changes direction, say in any other by isotropy.
Exactly, right? The point is, suppose you say that it's not in the x direction, it's not doesn't lie on the y equal to 0 plane, right? It goes away. Then it either goes towards positive y direction or the negative y direction, right? But which one, right? Because there is isometry, right? If it goes in the positive y direction, it's equally likely to go in the negative y direction, right? But the geodesics are not probabilistic, right? There are definite equations. You start with an initial condition and it evolves.
The plus minus coming out of the root.
No, that is a z. This is fine. That is not a worry, right? It's a question of these two. So here, similarly, if you start by saying that only the z starts moving, right? Only the motion is in the z direction. If you say that it is not this, right? Then that means at some point it starts deviating to in the xy plane, right? But once you say it start deviating in the xy plane, you have to worry about which direction it deviates, right? By isotropy, we know that there no direction is spatial, right, on the xy plane. If you start in the z direction, you better continue to move in the z direction. Yes, but initial condition I've already given. That is fixed. Given that initial condition, see, of course, if you change this, there is a different geodesic. I have already given this, right? Given this initial condition that it has component only along the z direction, right? Now I am asking, right, which direction will the geodesic move? That imagine that the initial condition you have vector is along the z direction, right? Now I am saying that if you take this, suppose you take x, y, z, right? At initially x and y are 0. So if it becomes x, y, z, that at some point it starts deviating from the z axis, right? X and y start becoming non-zero. But when x and y start becoming non-zero, they have definite values, right? So it starts moving in one direction in the xy plane. But no direction in the xy plane is spatial, right? Because of isotropy. Is that clear? So it, we have to restrict the. Exactly, that's right. We have to respect the isometry, right? So this initial condition, for example, doesn't violate the xy rotation, right? Rotation in the xy plane. So the geodesic should also be invariant on rotation in the xy plane.
We have disrupted the isotropy by introducing a vector.
Exactly.
I still have the rotations perpendicular.
Yeah, so the equations are all isometric, right? But initial condition you have disrupted, disrupts the isometry, right? Because you have chosen a particular direction.
So the isotropy I am left with, that should be
Exactly. 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 Right? Because that the potential doesn't deviate you from in one or the other direction, right? That's the point.
as soon as you put up a ball,
Exactly. Yeah. Is this clear? So if you try to look at the motion in the embedding space, right, it moves along this plane. Okay. The point is, if you try to do a 4-dimensional geodesy, now for the whole cosmology, right? You are starting a geodesic in the whole cosmology, and suppose the initial vector, right, the geodesic that you give, okay, still has this property. that Ni has only component, the x and y components are 0. Then the same argument will tell us that the 4-dimensional geodesic will also move along the same path, right? By isotropy. It cannot move away from move away towards x and y direction. Pardon? Exactly, move in the TZ plane. So the upshot of this, okay, is that if you take a geodesic in 4 dimensions and forget about the t coordinate, the resulting curve will be a geodesic in 3 dimensions. It's a completely general result, right? Because take a geodesic in 4 dimensions. Okay, it has to correspond to some spatial direction. The vector should correspond to some spatial direction. That spatial direction I can always choose in the z direction because you have isotropy, right? Because I can change my coordinate system so that the spatial direction is along the z direction. Right? And then by this isotropy argument, it will continue to move only in the z direction, leaving x and y 0. Right? Both the 4-dimensional geodesic as well as the 3-dimensional geodesic. Yes, tangent plane flattening it out, but the point is it is the same in 4 and 3 dimensions, right? This symmetry argument works both for 4-dimensional geodesic and 3-dimensional geodesic. Right? So if you have a particle motion in 4 dimensions, and if we just project it down to 3 dimensions, right? We forget about the time coordinate. Right? Doesn't matter what how much time it is taking to move. Right? We just want to follow the trajectory of the particle in 3 dimensions. In 3 dimensions, it will go along the geodesic. Yeah, that is the okay. You are reversing the statement, right? It is true that if this means that, right? But if you didn't have the isometry, you couldn't just take the original equation and say, okay, we just set t equal to 0, right? Because t is not 0. See, there is a contribution from the dt term, right? Okay. So we are making use of the isometry to give this argument that the 4D geodesics and the 3D geodesics, right? That once you forget about the time, they are on the same line in this 3-dimensional space. Not really, no. At this point, the time the arrow of time is not fixed. That's fixed by us. Right? We have decided t going up is future by convention. Yes, indeed. That's what it means. Okay. And we're going to make use of this. I mean, if we didn't make use of this, we are going to do a little more algebra, right? But this insight will be very useful, right? Suppose you want to know that we are here, there is a star, and some light comes from the star to us. Right? Which path will it follow on this 3-dimensional space, right? This insight will be very useful because that's the light comes from star to us along a 4-dimensional geodesic, right? 4-dimensional null geodesic. But once you know this projection onto a 3-dimension is a 3-dimensional geodesic, we already know the trajectory in 3 dimensions, right? That just makes life easier to do this kind of analysis. No, because the symmetry argument is independent of that, right? Whether it's null, time-like, or space-like, that depends on how much time it evolves along the trajectory, right? But as long as you forget about that information, the trajectory will always be along the geodesic. Okay, so I think I'll stop here and then discuss this next time. We'll see also how we apply it.
Suppose I don't have that big of an idea.
porous, that's yes. What is reactional line? Right, the dualism is very close. And
Initially, when we are starting, actually, we are using the data base. But so initial condition is suddenly there is some y, z, x, y velocity start switching on. But won't it be an anomaly?
exactly.
But that equation should prevent that.
Yeah, exactly. That's what I'm saying. It doesn't move away from it. But the equation is not symmetric in the x y. The equation should lie to the analysis, right?
Yeah, but we are from this metric
Yes.
that let's say if it is on, then there is no way that it shouldn't prefer a direction because it's actually there
That's
is still some residual symmetry.
Yes.
So it better not. I'm saying ki cannot switch on. Right? The geodesy equation.
Imagine a particle moving in a potential.
Oh, then it's not a geodesy.
Yeah, maybe the metric may not have that symmetry. Suppose the metric didn't have that symmetry. Then you may start in the z direction, but the metric may be such that it moves in the direction.